All right, we're now moving on to chapter 2. I know I whipped right through chapter 1, but chapter 1 really should be reviewed if you had any kind of physics in high school or any kind of science class from the middle school on. It was mostly just about things that you know about. Chapter 2 now we're going to start talking about one-dimensional motion. And you remember one-dimensional motion just means motion in a line. So you only have one dimension, it's just your position on the line. Now that line can be going up that way, any direction, but it is always in a straight line. That is one-dimensional motion. Now, one of the things that you hear is we use distance is equal to velocity times time. Which is true, but it's true only in a specific situation. It's only true if the acceleration is equal to 0. So let's talk about what velocity and acceleration are. Okay? And what distance, velocity, and time are represented. So, for example, velocity is equal to, and we're going to do an average velocity. An average velocity says that, oh, if I have a particle right here, and it's at position 1, and at some later time, it's at position 2, and this is going to be our x-axis. Then we'll call this position x1, this position x2. So those are two positions, and they're separated in time as well. So this is, when it's here, it's time 1, when it's here, it's time 2. If I wanted to get the average velocity of that particle moving in a line, right, no acceleration, then I would just say, oh, I'm just going to take its final position minus its initial position, which gives me the distance it traveled, divided by the final time minus the initial time, which tells me how long it took. So that's the position change divided by the total time, or the time that it took to do that. That gives me the average velocity, the velocity over that time interval. This is often written as change in x over change in time. If you haven't seen this before, remember it. I use this delta, means change. It always means the same thing. It always means final minus initial. Final minus initial. That's always what it means. So if you see that, that's what it means. Final position minus initial position. This is change in x over change in time. Okay? Now there's a difference when we have average speed. Average speed actually says the total distance divided by the total time is equal to your average speed. Why is that different? Well, let's think of it this way. Let's say I'm driving to a couple places. So I'm driving from point A to point B to point C, and then back to point A. So I made a triangle like this. Well, if I then calculated my average velocity, when I was at the initial position, I was at point A. When I was at the final position, I was at point A. So A minus A is just 0. My average velocity is 0. Because I'm back to the same position I started. But my average speed is not 0. My average speed would have to say, oh, I have to have this distance plus this distance plus this distance. I have to add those together and then divide it by the total time it takes to make the whole triangle. So that is a difference between average velocity and average speed. Okay? All right. And we want to get more complicated because we don't usually talk that much about average velocity and average speed. We want to talk about instantaneous velocity or instantaneous speed. And all you do to get that, so our velocity is equal to change in x over change in time. Well, the average velocity depends on how big a time interval. If it's like a few seconds, then the average velocity would be the velocity over those few seconds. Well, the velocity could change during that time. But if I make this time shorter and shorter and shorter and shorter, then the smaller I make this time, the smaller the x becomes, and they approach a point where you get the velocity exactly at that instant. Or we're going to change delta t into what we call an infinitesimal. Or instantaneous velocity is going to be let delta t go to 0. It never gets to 0, but if you're taking calculus, you get used to that, right? It's the limit as delta t approaches 0. Or what we're really going to do of delta x over delta t, and when you do that, this becomes a derivative dx dt. Okay? That becomes what we call the instantaneous velocity. We'll get back to that. What is acceleration? Acceleration is the change in velocity over change in time. Okay? And if you want instantaneous, you have to take the limit of this as delta t goes to 0, and this becomes of delta v over delta t. This becomes dv dt, or the derivative of velocity with respect to time. Okay? All right. I know this seems a little obscure, but I'm going to make this make more sense right now. Just write this down in your notes right now. We'll get back to this. Okay? In this case, we're going to say the acceleration is 0. What this says is 0. Delta t is still going to be a time interval, but the velocity is not going to change. So delta v, the final velocity, and the initial velocity are exactly the same. And if that's the case, then the distance something travels is just equal to the velocity times time, which you're used to. If you're going 50 miles an hour for 2 hours, you've got 100 miles. And so you just take your velocity times time to get the distance. This only works if a is equal to 0. If you're changing velocity while you do that, that won't give you the right answer. All right, so let's do an example. We have an example here, which is number 2.2 on page 35. And in this one it says, Bob leaves home in Chicago at 9 a.m. and drives east at 60 miles per hour. Okay? So Bob is in Chicago, and he's driving east at 60 miles per hour. Okay? And Susan is in Pittsburgh, which is 400 miles away. So we go over here, a total of 400 miles. And this is Susan, she's in Pittsburgh. And Susan is traveling west at 40 miles per hour. What we want to do is find out where they're going to meet. Now this would be really easy if they were going the same speed. They would meet exactly halfway. But they're not going the same speed, but they did leave at exactly the same time. They both left at 9 a.m. traveling towards each other, and we want to figure out where they're going to meet. So, we want to know where this is, so we need to know a distance, how far Bob travels and how far Susan travels. Well, since they're both going at a constant speed, we can just say that the distance is equal to the velocity times time. So I'm going to say distance of Bob is the velocity of Bob times the time. But notice I don't put a subscript on time because the amount of time Bob travels is going to be exactly the same that Susan travels. They're both going to go the same amount of time, and then they get to the same spot, they're going to stop. So they both do the same time. Susan is going a distance of d, Susan, is equal to velocity of Susan times time again. Okay? So we have these two equations. We know the velocity, we don't know the distances, and we don't know the time, so we can't solve those. However, we do know that the total distance is 400 miles. So we can say that the distance Bob travels plus the distance Susan travels has to equal 400 miles. Because whatever Bob goes, Susan has to go the rest, and the total has to equal 400. I can just add those together. But I can substitute. So this becomes 400 is equal to the velocity of Bob times time plus the velocity of Susan times time. But remember, they're going the same amount of time, so I can factor this out. So I'm going to get 400 is equal to time times the velocity of Bob plus the velocity of Susan. And then I'm going to divide by this to get time by itself, because that's what I want to figure out, is how long they travel. Divide both sides by that. And so I'm going to get, over here, time is equal to 400 over the velocity of Bob plus the velocity of Susan. Or, I'm going to take this as 400 plus 60 plus 40. 60 plus 40 is just 100. 400 divided by 100. Time is just equal to 4 hours. Because remember, this is in miles. These are in miles per hour, so we're left with the hours. That's not what they asked. They asked, where did they meet? Well, we know now exactly how long both of them drove. So I know the time, so now I can just plug it back into here. So the distance Bob travels is just going to be 60 times 4, or Bob travels 240 miles. And Susan is 40 times 4, or 160 miles. If I did it right, those two better add up to 400 miles. Does that make sense? Hopefully it does. Okay? So, these are how you do constant velocity problems.